That long discussion, but it still applies to additive manufacturing parts as well. But unless Boeing is certifying them, which in this case with digital alloys, Boeing is going to certify the parts under the STS supplemental type certificate that they hold. If Boeing certifies to the FAA that these titanium additive manufacturing parts are good, the FAA is going to say, fine, you're responsible, you're taking the risk, okay? If the plane comes down because of it, you're going to take the heat. And guess what's happening on 737 MAX? The FAA is not taking the heat. Well, they've taken a little heat, but mostly it's Boeing, right? Because they approved it. But you can get around the manufacturer through the PMA process, and you can either design a brand new aircraft component yourself and have the FAA approve it, or you can prove equivalency to the design standards. But the FAA cannot release what the design standards are to you. They have them, but it's proprietary information. Boeing gave them that information. They can't release it, but if you supply information, a stack of documents like this, they can say, yes, this meets the same criteria that Boeing gave us, or no, it doesn't. But it's not as if you can go through and ask, what doesn't it meet? Okay, they don't have to tell you. They can't tell you that because they might be violating the confidentiality. So it's an interesting cat and mouse game.
How does this work in other countries? Are they less stringent, more stringent? How do you move this stuff through?
Right, in the FAA, I think most of the equivalencies to the FAA work very closely with the FAA. Because, well, yes and no. The European Union, of course, has Airbus, and they're liable to give Airbus a little benefit of the doubt, like we'll give Boeing a little benefit of the doubt. But if you go to South America, they have their aviation authorities, and when they have a problem, it's not that they're not independent, but they're going to go ask the FAA what they think. And the FAA will send people in to do part of the accident investigation because they want to know what happened. They're charged with promoting safety, and even if the 737 MAX went down in Indonesia, where was the other one, Ethiopia or somewhere? Yeah, the FAA, there's an American on site, okay? And they were probably the ones who came back, merged the data from Indonesia and Ethiopia. Of course, the Indonesians and the Ethiopians are also dealing with it. We probably have more expertise in our FAA than Ethiopia or Indonesia. So they actually work very closely. They have to. Because none of them have enough staff to do it all. And they rely a great deal on the manufacturers. When there's a failure, you'll hear that the National Transportation Safety Board went in. They're there the next day. Pipeline explosion, NTSB is there. A ferry sinks, NTSB is there. A railroad disrailment, anything where there's transportation involved, we have a National Transportation Safety Board. They're charged with going in and doing the investigation. They don't have all the expertise to do that. They will invite in people from the railroads or the manufacturer of the railroad equipment, and they will come in and they'll ask them questions. And they have subpoena power. If you don't answer the questions, they'll get it, okay? They'll go to the judge and they'll force you to give it. So there's sort of cooperative mode here. Is it completely cooperative? No, okay? But, the companies aren't going to say, oh, well, we screwed up, okay? But these guys, the U.S. Engineers at NTSB are not all stupid, okay? And now we have a Chemical Safeties Board, which models after the NTSB. NTSB's been around for 50 years. There's a big explosion in a chemical plant in Texas. CSB's in there. Write big 100-page reports on why it happened. It's sort of like OSHA investigations of an industrial accident. Sometimes they're pretty good, and sometimes they're pretty bad. It's just dependent on the quality of the government investigator writing the report. Okay? Okay, other questions? Did that answer your questions? So, see, I actually think learning about these investigations and how it really works is interesting, but it's not as scientific and technical, it's more political, okay? But it's real, okay? Okay, no other questions? Then, okay, I passed, hopefully, the sign-in sheets. And most of you have attended enough classes, that's not going to be an issue. If we look at, I might as well run it if you haven't seen it. So they're not going to make just simple parts, they're going to make some part. This is the digital alloys. This is from their blog site. And they actually have taken a Boeing part, and Boeing's done this analysis, and if this is to make 5 kilogram titanium high buy-to-flight, remember buy-to-fly ratio, 5 kilogram part, that's a fly part, it's 5 kilograms. 5 kilograms is probably going to fit within the size of a soccer ball or something. And making 100 parts, not just one part, but 100 parts. You know, you're not making one of a kind unless you're a spacecraft. And what we've got here is for machining, yeah, you can set up your CNC machine tool and stuff, and this is just to do rough machining, 40 days, okay? Remember, you're going to machine away probably 90 or 95% of the 5 kilograms. So you're going to make 500 kilograms of parts, but you're going to multiply that by 20. You got 10,000 kilograms. You got, or is that right? Anyway, you can figure the math if I did it wrong. But you got a lot of chips, titanium chips at the end. And it takes time to do that, many, many days. This is for jewel printing, but if you could do it by binder burnout or something else, you would also you get something similar, 17 days. Well, 40 days versus 17 days, and you start doing the math on all that, on the cost, and you're going to find that he did energy, and CNC machining for a single part is not very much energy. I don't think the energy thing is all that interesting. But if you get into the actual, well, I guess the real thing here is the time savings, okay? You're going to find that additive manufacturing of these parts is a lot cheaper than manufacturing the old-fashioned way, where they just hog it out of a big hunk of titanium and make a little bitty part, okay? Remember the Aladdin movie? You know, great, tremendous power, little bitty house to live in for Aladdin? Oh, sorry. You have to have grandkids, maybe. Okay, so then he went on. Part 8 is about powder bed fusion, which is something like laying down a layer of powder, coming along with a laser or electron beam or an arc or something. And now we get part size. So their process will do things that could be as big as a soccer ball, which is your 5 kilogram part. Some of these things, like binder jetting, where you're actually squirting powders and adhesive together and building something up, okay, you can make a golf ball, okay, or a tennis ball or something. If you want to make something that's, you know, substantial in size, a meter, you're going to have to be into directed energy deposition, and I'll show you something on that in a little bit. Here's an example from the General Electric area. An aerospace fuel nozzle, very complex part. Yeah, it's a structural material, but it's a functional material. Remember I told you the other day when you're doing pixel by pixel, you got to have a functional advantage. Just strength of, you know, tensile strength, yield strength, and elongation are not going to cut it. You can usually make those things other ways. But when you need all these little holes and bosses and things, previously made from 20 different parts. And so there's a tremendous cost savings there. If you go to directed energy deposition, there's powder and wire deposition. Well, this is my technical community where I got my tenure was welding, of course. You wouldn't necessarily know that, of course, but this is the types of stuff that I would do and do research on and look at heat transfer and whatnot. But you basically have a wire you're feeding in, like a welding wire. You've got an arc, This is a gas tungsten arc. And you basically just put down little drops of metal about the size of a weld pool so you can make something a meter in diameter. Okay? If you keep going to, I want to keep going, let's see. Probably have to tell it to stop. This is laser, and this is all on their blog. I just stole these right off the blog. So you've got a laser you're feeding powders in, and you're making a cylinder out of powders, okay? So far as that goes. And that's probably about those both, well, the wire EDM was slowed down from real speed. This is probably about real speed, okay? Now, what do you get if you look at deposition width in millimeters versus print speed in kilograms per hour? If you have nice small pixels, less than a millimeter in size, you're not going to put down a lot of kilograms an hour. In fact, you're going to be talking ounces per hour, okay? If you have some big weld pool and you're going to be making something the size of a meter, yeah, you got 10 kilograms an hour. And you know what? That's about the fastest any welder can weld. If you go through and figure out the economics of a welder doing things on a weld site, you look at how many pounds per hour or kilograms per hour a welder can put down. It's a few. For a gas tungsten arc, it's around 7 pounds an hour is a max. But for other processes, you might get 15 or 20 pounds an hour. Okay, well, there it is. Okay? It's not any faster than just laying it up as weld beads. And we've been doing that to add things, additive manufacturing for years. In fact, that's why I brought this, and that's why I drew this picture. Anybody recognize this? It's a turbine engine, okay? You got a center shaft, you got some compressor blades, and you got some combustors where you add the fuel and the compressed air, and then those go past the turbine blades. Those turbine blades spin this whole thing. As they spin this whole thing, the compressor blades compress the air by about a factor of 30 in volume, but it's going up in temperature, so you get to like 1,000 psi pressures. But you got a problem. You don't want any blowback when you've got high pressure here and atmospheric pressure out here. If you don't have a good seal between the shroud and the blade, you're going to be losing efficiency as the air goes the other way. So what do? Well, the first thing we do is we make a honeycomb. This is a shroud, actually a piece of a real shroud that had been in service. And this is not the blade that goes with it, but the blade's going to be spinning at 20,000 RPM. It's going pretty fast. And it's going to be going past this thing, and we actually make it a nice, soft, compliant honeycomb structure that will wear away. As the blade creeps, it's working at higher temperatures, and it gets longer over time, over 30,000 hours of operation. It gets longer, and as it gets longer, it just cuts into the shroud, and it keeps a good seal. What do? Well, these tips wear out, and we want to recondition these blades. These blades, not this one, but some of the fancier blades, could cost $2,000 or $3,000 a piece. Okay? So what do? We go along with these little directed energy deposition. We never called it that before advanced additive manufacturing, but they actually called it dabber welding. The Air Force went to Tulsa, I think Tulsa, Oklahoma, maybe it's Oklahoma City. They have a big repair facility for their engines. And they would just put on little carbide composite coatings on the tip so that it intentionally cuts into the surface as it's spinning at high speed. We've been doing that for 50 years, okay? That's additive manufacturing, folks. It's done on the original parts, it's done on the repair parts. We do all kinds of additive manufacturing because we're saving a $2,000 blade and letting it go for another 30,000 hours. There's a lot of value in that, okay? So that's another place of additive manufacturing is wear and maintenance and things like that. And then they go through binder jetting, and we won't go through that. Now, this came up the other day, is how big are these parts and do they shrink if you start out with a powder compact that's 50% voids when you just glue powders together? Well, once you heat it and center it, something that is this diameter or this diameter shrinks down to this. These are not huge parts, but this is a compressor blade or turbine or whatever. And it really doesn't have great geometry control. I mean, it looks good, but balancing this, because it's going to spin at 30,000 RPMs, okay, for something that diameter, it's got to be balanced, folks, okay? It's not going to be easy. Typically, we cast these things, but anyway. We don't do it by additive manufacturing. This, I think, is a demo. I'd be surprised if that's in production. Okay, and then the last thing that Alec Huckstep has put together is surface roughness. All kinds of different surface roughnesses. This is wire directed energy depositions. These are just a bunch of overlapping weld beads. This is that jewel printing, which is pretty rough. You've seen that, passed it around. Binder jetting can be pretty fine. Powder bed, which is sort of like the desktop metals, is better, a lot better than jewel printing. And here's the sizes, or these are not dimensions, but he's got another graph that I haven't really studied, but basically it shows that the surface roughness in microns goes from 100 microns for that weld bead down to 5 microns or less for the different processes. So different attributes for different processes. And here's a example that he had in there. Another, I think it's probably titanium, it could be stainless steel part, done by a directed energy deposition process on a plate. The plate actually becomes part of the final machine part. There's lots of machining, but it cuts down your machining so far as that goes. And that's sort of the end. Yes?
So with the heat treatment, we see the geometry change.
Yep.
So in the industry with aerospace that has such tight tolerances, how do you account for the geometry change? Is it possible to incorporate?
From the sintering process you're talking about?
Or like this, post-process?
It's one of my problems with the sintering process, okay? If I come to the conclusion that aerospace manufacturing is the sweet spot, and I need ultra precision for the aerospace market, I don't think the powder sintering process is any good for that. They think they're heading towards the automotive market. I think they're kidding themselves, okay? But, maybe they're going to write. They're going to have an IPO and they're going to be faculty members in this department walking away with $5 or $10 million in their pocket. I don't have that. So maybe they're a lot smarter than I am, but your grandmothers are going to end up with a lot less in their pension fund 10 years from now. Okay? Because someone's going to take and buy some of that IPO, put it in the pension, and over time you're going to see it just drop down, in my opinion. That's my opinion, okay? It's just an opinion. But you can make your own choice right now. You now know enough. And in fact, okay, so we spent 6 hours talking about actually not even that, because I had tangents that not about additive manufacturing. Whether it's additive manufacturing of metals or whether it's high temperature superconductors, your MIT students, you should be able to study the technology on your own for 2 hours and know more about it than the person who wrote the article in the Wall Street Journal that says it's a wonderful new technology. Okay? I guarantee you, 2 hours of intense study, and I would have loved to have given you papers to write where you could, take a topic, but I found it's easier just to let you pick a topic that you like and you'll study it, okay? But you become an expert within 2 hours on a topic that you're interested in. Well, if someone is trying to, let's say your grandfather left you $100,000 to invest in some new startup at MIT, hopefully you wouldn't just go to the first one that's walking down the infinite corridor, right? You're going to do some study, and hopefully you'll spend 2 hours studying the technology, maybe rejecting it, then you got to go study another one for 2 hours. In the end, maybe you'll spend 10 hours to select one out of 5, okay? but you ought to be able in 2 hours to learn quite a bit and do critical thinking if you know some of the principles. One of the principles I taught you in the beginning, the value of a pound saved in an automobile is $2 over the life of the vehicle. In aerospace, it's $200. As I always say, they have vice presidents at American Airlines figuring out how many magazines they're going to put on that aircraft, because magazines are heavy, okay? And at $200 a pound just to carry around something people aren't going to read, okay, that's a lot of money. On aerospace or space technology, you know, Elon Musk, he wants to die on Mars, but he doesn't want to do it on landing. That's one of his quotes. I think we should send him to Mars, okay? Never mind, I won't say any more. Okay. First of all, it's a 1 year trip, one way. Okay. And at $20,000, the people who are going to colonize the moon, let's not go to Mars. They're going to colonize the moon at $20,000 a pound. Well, let's say the space shuttle was supposed to reduce the price of a pound in orbit. That was in $1970 from $10,000 a pound to $1,000 a pound. Let's say we can do it for $1,000 a pound, okay? SpaceX or whatever is going to get payload in orbit for $1,000 a pound. You know what it's going to cost for me to buy a ticket? I would be incentivized to lose some weight. Okay? $1,000 a pound, okay? And once you get to the moon, you might need some other things there to live off of, right? Which is why NASA is looking at, well, can we dig up moon rocks and process them to make ore, you know, the ore to make metals, and where are we going to get the energy over there? Okay, well, we got solar energy. Yeah, okay, fine. You start looking at all the things you have to do, and you were at NASA Langley, and they got hundreds of people looking at how they're going to do this, right? How they're going to weld things in space, you know, and how they're going to process things in space, how they're going to repair things. You know, and I heard a faculty member, I was in a alumni thing in Philadelphia once, and I was talking about whatever I was talking about. We had a young faculty member, she's not so young anymore, but this was 25 years ago. I think she was close to tenure, and she has tenure now, and so has a very distinguished career. And she was talking about the mission to Mars, okay? And she was saying, you know, and we can afford this. We spend as much money on potato chips each year as we do on a program of, which would be about $2 billion a year, she was claiming, to go to Mars over the next 20 years. Okay, $40 billion. Well, first of all, I don't think it'll be $2 billion a year. I think it'll be $20 billion a year. You know, it'll be a $400 million. But anyway, well, let's take her $2 billion. And I leaned over to the person next to me. I said, if you did a poll of all the people in America, would they be willing to give up their potato chips for a trip to Mars? I think I know how that vote would come out. Okay? I think it comes out every day in the grocery store. Okay? There's a lot of other things we need in this country that we could spend $400 billion on, in my opinion, for a social good, than to send Elon Musk to Mars, okay? I'm sure he'd enjoy it, and he can die there, okay? Anyway, so I have my opinions about some of these things, which I think I just gored NASA, but or their ox anyway. They probably could defend themselves and talk about why it's useful and stuff. And you can look back at putting a man on the moon. It brought us gallium arsenide, which is one of the great materials advances. I admitted that, okay, and LEDs and all those other things, GPS and things. A lot of things come out of that. But you could also spend that money in other ways and develop sustainable, environmentally friendly technologies. Maybe we would have had solar power 30 years ago if we had invested some money in solar power 30 years ago. Okay? Anyway, There's lots of choices, and they're often made for political reasons. Any questions? So let me just say that this actually is the next lecture with Alex Huckstep next Thursday will be the sixth lecture, and we're supposed to meet on Wednesday, but I have to go to a trial in Houston, and I never know when I'll get off the stand. So let's cancel class next Wednesday. Let's do Alex Huckstep next Thursday. I'll have Jerry put this on Stellar. And if we need another class after that, we'll schedule a class in October, okay? But I'd rather do that than be sitting there on Tuesday evening trying to get the word to you that we do or don't have class on Wednesday. I think it's just easier. And if I am here on Wednesday morning, well, I'll find something to do, and you can find something to do on Wednesday morning. Now, what I'd like to do on Thursday with Alex is let you ask whatever questions, because he's lived this, okay? He put these blogs together. I think they're excellent and balanced presentations of what the advantages are on different types of additive manufacturing. He, of course, is in the business, and so he is promoting his, but he has, a lot of his stuff came from real data. In this case, you can see all the Boeing interest, and you're getting Boeing's data on the parts. But I'd like you to think about if you had an additive manufacturing idea and you were doing a startup, what would your strategy be? What industry would you go after? What material would you go after? Why did we not talk about aluminum? Because aluminum's got an oxide and it's hard enough to weld. Try to take little particles of it and join them together is going to be extremely difficult. Titanium doesn't have a surface active oxide that's hard to get rid of, so titanium is nice. Stainless steel is not bad from that point of view. Why haven't we talked about copper alloys? You could do copper alloys or brasses, but what's the volume there, okay? The volume is in steel, or if you're going to aerospace, you're looking at aluminum or titanium, or you might get out of metals and you might get into composites. So you might talk about plastics additive manufacturing, which probably has a number of applications in the aerospace industry to make excellent composite structures, or maybe you've got an even better idea. If you can figure out how to repair those composite structures, because that's one of the big Achilles heels for composites in aerospace. We can make them, but we sure don't know how to repair them very well. And they do get dinged up every now and then. Look at the space shuttle, okay? So I'd like you to think about, do some critical thinking as if you were going to invest or you have a startup. What types of materials, processes, industries would you go after? If you don't know where you're going, any road will take you there, and it probably won't be profitable. Okay? Okay, any questions? So here's my soapbox.